Hello, everyone. Welcome. I'm Jennifer Nyman. I'm a principal at Geosyntec Consultants and coordinating the webinar series. I have the pleasure of facilitating today's event. The webinar today features DoD-funded research to demonstrate advanced microgrid control algorithms. First, Dr. Fran Lee of the University of Tennessee will discuss model-based analysis and data-driven implementation for control for microgrids. His presentation will be followed by a brief question and answer session. Second, Dr. Debor Karsai of Vanderbilt University will present on how foundational technology for decentralized microgrid control can be applied in a field environment. His presentation will also be followed by a question and answer session. We will conclude the webinar today with a Q&A session featuring both of our speakers. The next slides provide some instructions on optimizing your webinar experience. If you haven't done so, download Zoom, the link shown here. If you can download Zoom, you can view the slides using a compatible internet browser and creating a free Zoom account. If you can't view the slides or if your screen freezes, try keying Control as well as F5 to perform a hard refresh. If you are connecting the audio through your computer and have any troubles, click on the arrow next to the Join Audio button and select Test Speaker and Microphone, and then follow the prompts as they appear on your screen. If you continue to have any difficulties, call into the conference line shown here. You can also submit a comment using the chat box, but please use that chat box just for comments related to technical difficulties. The Q&A box should be reserved for questions. And in case of continued difficulties, you can download a PDF of the slides from the webinar webpage, and you can call into the conference line provided to you in your webinar registration confirmation email. We will also be live streaming the webinar on the SERDP and ESTCP YouTube channel at the link shown here. Today's broadcast is listen only. You may submit questions by using the Q&A box on your screen. You don't have to wait until the Q&A period to submit questions. And in fact, we would encourage you to submit questions in advance of that session. When you submit your questions, add your organizational name at the end of your question so that we can identify you. And with that, I'm going to introduce today Dr. Eric Suckerbaum. Eric is standing in today for Mr. Timothy Tatro, who is the ESTCP Program Manager for Installation Energy and Water. Eric will provide the overview of SERDP and ESTCP. Eric, please proceed.
Thanks so much, Jennifer. I'm happy to welcome everyone to today's SERDP and ESTCP webinar. Slide 11, please. SERDP is the Strategic Environmental Research and Development Program established in 1991 by Congress as a partnership between the DoD, the Department of Energy, and EPA. SERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately impact real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under SERDP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. SERDP and ESTCP are complementary programs, with much of SERDP research occurring at the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. Slide 12, please. There are several environmental drivers for the type of work funded by SERDP and ESTCP, with the underlying objective of sustaining DoD ranges, facilities, and operations. This, as you can imagine, is a broad undertaking. It takes the form of looking at maritime sustainability, threatened and endangered species, climate impacts, unexploded ordnance and munition constituents, as well as other environmental drivers. Slide 13, please. One key environmental driver is the reduction of current and future environmental liabilities. This involves addressing contamination from past practices, including impacts to groundwater, soils, and sediments, UXO contamination, and developing management approaches for contaminants of emerging concerns. The second part of this is pollution prevention, with a focus on eliminating chemicals of concern or hazardous materials in manufacturing, maintenance, and operations of our installations. Slide 14, please. We have several main focuses for research and demonstration at SERDP and ESTCP, as shown here. Slide 15. As mentioned earlier, technology transfer is very important within the SERDP and ESTCP programs. Technology transfer efforts include the development of videos, training workshops, and guidance documents. The webinar series is a substantial component of our technology transfer efforts. Slide 16. Our webinar series highlights research and demonstration efforts from all of our program areas. Upcoming topics include characterizing and treating PFAS source zones, water resilience projects, and others. Coming up in September is a series of 2 joint WP and ER webinars on managing AFFF impacts in subsurface environments and assessing novel and commercially available PFAS-free foams. Registration is now open for webinars through early 2023. Slide 17. You can find additional information about upcoming webinars at this link. All past webinars are archived and can be accessed also using this link. Next slide. Lastly, please save the date for the 2022 SERDP and ESTCP Symposium, which will be held November 29th through December 2nd in Arlington, Virginia. This event will showcase the latest technologies that enhance DoD's mission through improved environmental and energy performance. Finally, I would like to remind you that a copy of the presentation of today's session can be downloaded from our webinar webpage. We would appreciate it if you can please take a moment to complete the survey that will pop up on your screen at the end of the webcast. With that, I hope you enjoy the webinar today, and I'll turn it back over to Jennifer.
Thank you so much. It's now my pleasure to introduce Dr. Fran Lee. He is the James McConnell Professor at the University of Tennessee, Knoxville. Fran is the campus director of the Center for Ultra-Wide Area Resilient Electric Energy Transition Networks, a National Science Foundation and Department of Energy Engineering Research Center. He's also the editor-in-chief of the Institute of Electrical and Electronics Engineers Open Access Journal of Power and Energy. Fran's research interests include renewable energy integration, demand response, power markets, power system control, and power system computing. He received degrees in electrical engineering from Southeast University in China and a doctoral degree in electrical engineering from Virginia Tech. Fran, please proceed.
Thank you, Jennifer, for the introduction. Good morning or good afternoon, everyone. Thank you for joining my webinar. The title of my presentation is Response Controllable PQ Control for Microgrids, Model-Based Analysis and Data-Driven Implementation. Okay, so here is the presentation outline. First, I'll talk about the challenges present in microgrid. Then I talk about response controllable PQ control algorithm. Next, I'll discuss a little bit about model-based analysis and the data-driven implementation, followed by conclusions and discussions about the benefits to DoD. This slide shows some challenges about the device in the microgrid system. Typically, they're controlled separately based on pre-configured control gains. For microgrid control, typically we want to achieve some features like resilience, plug and play capability, control coordination, and also mode transition. This diagram shows a response controllable PQ control. So typically in a system with main grid on the left and then the microgrid shown here, if there's some response, we want to inverter-based microgrid to respond following some ideal trajectory. So in other words, our key idea is in the event of a disturbance, we want to keep the response following ideal, maybe predefined trajectory. So then the performance will be always consistent. And also if we move the microgrid to a different place or move some of the controllers to a different system, the response will be consistent and we don't need to do any additional tuning of the control parameters such that we can achieve a plug and play control. Okay, so here is the diagram for inverter-based DG connected to the grid, and on the left it shows the control blocks, and on the right it shows the ideal response and a virtual response. Typically, the actual response needs a dynamic KPKI for the PI controller, which is typically used in inverter-based control. Traditionally, engineers tune KP and KI for when applied to a new system. And then once this manual tuning is done, then that's it. The KP and the KI are pretty much constant. But here, the idea is to maybe KP and the KI can be dynamic, meaning dynamically changing with response to time. So that's why we have KPT-KIT here, such that the response is very consistent, always following the ideal trajectory. No unexpected spikes or sluggish response. Okay, so to achieve this, we perform model-based analysis first. So based on our analytical derivation, we obtained the dynamic KPT and KIT as these two equations, basically KP0 plus KP1 times E T or negative T over tau. So that basically shows a exponential decay function. So which means that even though KP and KI are dynamic, the function of T, it can be narrowed down to this expression. And then now we need to get the two constants, KP0 and KP1 for KPT, and also KI0 and KI1, those two constants for KIT. So this with this KP0, KP1, KI0, KI1 pico response of inverters can be accurately controlled following ideal trajectory. So although we can perform analytical expression to get accurate control parameters, but many times the system parameter may not be accurately available, or sometimes just not available. So then we want to use deep reinforcement learning to obtain the coefficients. So here kicks in the deep reinforcement learning, and I want to maybe briefly mention the achievement of AI or reinforcement learning in recent years, as some of the literatures in AI and in showing that some like achievement like AlphaGo, playing a very complex board game, beating human championship, which is considered a great epic achievement, 30 years ahead of the many scientists' expectation, and also Alpha Star for the real-time strategic game StarCraft, and also reinforcement learning-based magnetic controller for nuclear fusion. All those literatures can be found in top-notch journals like Nature and Science. So the achievement of reinforcement learning or deep learning is significant. Here I want to mention a little bit about data-driven implementation, specifically the motivation. Like I mentioned earlier, so sometimes it's difficult to model the whole system, or system parameters are not always readily available and or accessible, and when accessible, they may not be accurate. Also, we want to autonomous operation free from tedious tuning. And when we move to the controller to different system, we wanted to plug and play. Don't need to re-perform the tuning work. We applied twin delayed deep deterministic policy gradient algorithm, or TD3PG algorithm, which is considered an upgraded version of DDPG, or deep deterministic policy gradient. So with twin critical networks and delayed update of a target and the policy network, and also it has the feature of target policy smoothing. Here, this slide shows high level idea of deeper reinforcement learning. On the right, that's the environment, or the microgrid. So here at the bottom, that's a action. At the top, that's a buffer. So basically, when there is some action taken, then the environment will behave based on the new action, and the parameters or data will be sent to actor network. So it will recommend new actions. Then the critical network will evaluate the new action, obtain the Q value. And this is in comparison with the older AI technology like Q table. This critical network basically gives replace the sort of a lookup table, Q table, and then give evaluation, and then send back to actor network for another round of evaluation of a new actor. And all this actor final action will be sent to the environment, and then the new results will be obtained and sent to the actor network again, so till it converges. Okay, so we applied the model-based derivation to guide our deep reinforcement learning. So you can see that here's on the top, the blue curve shows the training progress with the model-based idea. So basically, with the two equations I showed a few slides back, the training will be a lot faster. And the bottom red curve shows the training progress without the equations, or without the guide of the physics. So then it's almost like a random search of the different KP0 and the KI parameters. So then, to search for different KPT and KIT parameters. So then it's almost like a random search. So then it will take a lot of more time to get it done. And in our diagram, it shows that here, after 12,000 episodes, model-based training is already done, converged, and the without model-based analysis, the DRL training is still not converged. Okay, next page. And I want to mention that inverters can be freely assigned a response time because inverters are electronics and very fast. It's different from synchronous generators, which has the inertia. And so here we can set the decay time constant to 0.1 second, 0.2 or 0.5 seconds. You name it. It can respond with exponential decay. So, well, that delta P will be a exponential decay. So basically you flip this diagram. It shows the response can be defined based on whatever we prefer. Okay, so that's then you may ask what the time constant should be. That's really a decision maker's choice. We will provide some high level discussion on that later on. Okay, so here it shows some simulation studies with a large time constant for scheduling change. For example, when we perform maximum power point tracking, or we perform the 5 minutes of scheduling change, we can take it's recommended to take a larger time constant. So then we will have a smoother response with a smaller overshoot as shown here by this greenish curve. Then if we have unexpected large disturbance, then it's more recommended to take a smaller time constant such that we can achieve faster response to pull the system back from the disturbed state. Okay, all in all, this choice of the time constant is the decision maker or designer's choice. And we want to show that the after well-trained parameters is done, the system can respond to almost any time constant. Here is a demonstration on the current, what called a current hardware testbed, or HTB. It's quite a unique power hardware in the loop testing facility at the University of Tennessee and our current research center, and also integrated with the RTDS simulator eventually. This is a user interface with the HTB demonstration. If you haven't been to the current research center's test bed facility, you may want to stop by Knoxville if you get a chance and take a look at our virtual control center. It's a pretty nice and significant test facility. Also here, this is the screenshot from our HTB demonstration, and the details, well, the details on the right diagram is shown here. So here we have 3 demonstration case. The first is a PQ reference change. So basically around T1, first, second, then we change the reference, and then later on around 2 to 3, 4 seconds, we change the reference back. So then you can see that it follows here, the P follows the ideal trajectory based on different time constant here, and then later on the reference drops back to the nominal value. So then you can see that the response follows exponential decay, and the based on time different time constant the response speed is different. Okay, scenario 2 is load change case. Basically, initially there is some load increase such that the frequency will drop. And then later on, around 1.5 seconds, all the controllers will respond and bring the frequency back to nominal value. And then around 2 to 4 seconds, the load will be back to the original value. So there's a frequency jump here, and then the controller will bring the frequency back to 60 hertz following the exponential trajectory. So here I want to mention this looks like the load restoration happens at different time. This is basically experiment settings such that we can show them in one figure without too much overlap. Okay, the third case is the generation loss case. Initially there's a generation drop, so then the frequency drops, and then later on their generation is back, so there's a frequency jump. And for both cases, you can see that the controller performs as expected, bring the frequency back, and also the corresponding power change follows the predefined ideal curve. Okay. Concurrence response controllable PQ controller improves microgrid performance. So we use a time varying gain PI controller to ensure the response tracks the predefined or ideal PQ trajectory. We use the model-based analysis to simplify control complexity and also making reinforcement learning more efficient. This is very important. If, like one of the diagrams shows, if we don't perform the model-based analysis as a guideline for our reinforcement learning training, then it's more like a random search in a large searching space, so it will be a lot more inefficient. With model-based analysis, it basically guides the training, making the training more efficient. So this, I think, is the difference between AI implementation with domain knowledge versus without. Okay, so I think it's good, always it's good and reasonable to apply our domain knowledge to improve the AI or data-driven approach. Okay. Right, and also overall, this data-driven implementation makes the controller more friendly to end users. So then the engineers, field engineers, don't need to tune parameters. Okay, all right. So benefits to DoD programs. This is applicable to microgrids with heterogeneous assets and mission-dependent nodes. And it will smoothly accommodate new DER load additions and facilitate the integration of DERs and coordinate different type of generators. So in environment of DoD mission, the microgrids could be reconfigured every day or maybe moved from one place to the other. So then under different environment, this proposed data-driven controller will be plug and play, free of tuning. So for a new system, you just plug it in and you don't need to do anything. It will learn on its own. Cost reduction from controller design costs, deployment costs, and reduced potential interruption cost. Okay. Acknowledgement. I want to thank my two GRAs, Bushing and Jingling, and also I want to thank two co-PIs at Missouri University of Science Technology. That's Professor Rebo and Professor Jonathan Kimball, and their GRAs operate snaps. And also I want to thank another co-PI, Professor Han-Tao Cui from Oklahoma State. Okay, here are some additional resource and information related to this work. And this is my contact information here. And I guess here's a Q&A session. I saw some questions in the chat. Let me take a look at this.
Thank you, Fran, for the presentation. And this is Jennifer again, and I want to encourage the audience at this time to submit their questions. To the audience, please use the Q&A box, the box that's a feature of the Zoom screen to submit questions. But yes, Fran, we have a number of questions. The first is about what you were discussing on slide 34. You mentioned a time constant for inverters, and you talked about their response being either slow or fast. So can you expand on that? How many seconds or milliseconds is fast or slow?
Very, very good question. Actually, we talked with utility engineers. First of all, I want to mention this. Well, I'm a power system person with power engineering background, and the controller and the inverters electronics could be a lot faster than the traditional synchronous generator response. And however, sometimes we don't want too fast. For example, you want maybe give the protection device a chance to clear the fault, because maybe the fault is a momentary fault. So here in the simulation, certainly we assume it's a sustained fault. So typically, when the utility engineer recommend 0.1 seconds as a threshold. So you don't want to respond too fast, faster than 0.1 seconds. So that's why in our study, when we test the different time constant, 0.1 is the smallest value, although we could be smaller than that. So that means if you want to fast, don't be faster than 0.1. And also another thing the designer may want to coordinate is with the primary and secondary frequency response of the grid, especially if you have synchronous generators in the system. So for example, the primary frequency control takes a few seconds, and then secondary frequency happens at the tenths of seconds or minute level. Yeah, so that's the basically guideline.
Okay, thank you so much, Fran.
Mm.
Can you say a little bit more about the connection between new distributed energy resources, load additions, and your approach that is model driven?
Okay, my understanding of the question is that when there's a new load added to the system, do I need to do anything to the controller? The answer is no. We don't need to do anything, because with the new system or new configuration, the controller will learn from the data or measure data, and then it will reconfigure its own KPT and KIT. As you know, the biggest difference of this one versus more or less traditional control is that in traditional control, your KP and KI is fixed. So I have talked with my utility engineer. I asked them, oh, what if you have a different load or or maybe move to a different system? Their answer is that, well, if it's a really significantly different, we need to redo the tuning. If a minor change, we probably don't need to redo the tuning. And in our approach, we always, the controller will always follow the ideal trajectory. So based on its own learning approach.
Okay, understood. Thank you, Fran.
Okay.
Next, would you let us know, are there any rules for designing the PQ trajectories for microgrid inverters?
Hold on a second. Could you repeat the question?
Sure. Are there any rules for designing the PQ trajectories for microgrid inverters?
Oh, okay. Yeah, good question. That's somewhat similar to the previous question, like faster or slow. So basically, my recommendation is don't be faster than 0.1, and also be sure you coordinate with the grid protection device settings. You don't want to intervene with them too much. Yeah.
Okay.
Yeah.
And are there any limitations with respect to the computational power that might be needed for the deep reinforcement learning if this is deployed widely?
Not really. Then in the current technology, it's pretty sufficient based on our testing. Yeah.
Okay, great. And I think we have one last question for you, Fran. To wrap up, would you reiterate, why do we still need model-based derivation when using model reinforcement learning?
Good question. I think as one of the slides shows, without a model-based training, it's more like you search like a random trial and error, and then you could gain some knowledge and gradually converge, but it's much less efficient. Model based training or analysis will utilize the information in the control the whole system and significantly shorter your training. So basically, it's like a huge search in space, and a model based training will find the kind of an optimal training path to get it to converge. So it will shorten the training significantly. Yeah.
Okay. Well, thank you very much, Fran. And Fran will be joining us again at the end of the webinar for a couple of additional questions. So if you have any more questions for him, feel free to submit those. Thank you.
Thank you, Jennifer.
All right, now we'll move to our second speaker, Dr. Gabor Karsai, who is a professor of electrical engineering and computer science at Vanderbilt University, and a senior research scientist and associate director at the Institute for Software Integrated Systems. Dr. Karsai conducts research in the model-based design and implementation of cyber physical systems, programming tools for visual programming environments, and the theory and practice of model integrated computing. He has managed several large DARPA projects related to advanced scheduling and resource management algorithms that resulted in a technology transitioned into all tactical aviation squadrons of the US Marine Corps. Dr. Karsai received multiple degrees in electrical and computer engineering from the Technical University of Budapest and a doctoral degree in electrical and computer engineering from Vanderbilt University. Gabor, please proceed.
Thank you for the introduction. So my talk is about this integrated microgrid control platform that we are developing and experimenting with. Okay, so this is the outline of my presentation. I'd like to introduce the objective of the project, the technology that we are building on, what our results are, summarize the benefits to DoD, and finally conclude the talk. So our objective is to show how distributed microgrid controller technology is applicable in the field. So this is probably a new concept because traditional microgrid control is pretty much centralized. And in our case, we are deliberately looking for decentralized distributed solutions. The project has two ingredients, so to speak. One of them is the actual control algorithms. The other one is a software infrastructure that allows the distributed implementation of these control algorithms. So moving ahead, the microgrid controller that we are envisioning is a completely distributed system that is using advanced algorithms, and it is implemented as a distributed software application. So it's like a way of implementing algorithms, but not on a centralized controller, but on nodes that are directly connected to power system devices, but they are also connected to a local area network where these computational components can exchange messages. And this is the very high-level overview of what we envision. Every one of these little REAPS nodes, REAPS is the name of the underlying infrastructure, acts as a bridge between the physical device, which is of course connected through the power connection, as well as the logical network that connects the different computational elements. So moving ahead, the other component that we are using is this what we call the resilient information architecture platform for the smart grid that came out from a previous ARPA-E project. So it's kind of an operating system. It's like Android for phones or iOS for the Apple phones. And it acts as a software layer that helps with implementing complex distributed systems and distributed algorithms. It provides certain services for security, but also services for fault tolerance, distributed coordination, time synchronization, and other features that are necessary for building distributed applications in an industrial context. So what we run this on, these are small embedded industrial computing nodes. The picture what I'm showing here is based on a Raspberry Pi module, but it's an industrial DIN rail compatible device that you can mount on a power system device. And it has the necessary network connections as well as connections to the local hardware elements. These nodes are usually coming under the IoT gateway or embedded computing nodes, and there are many choices for such devices in the market. These are, of course, industrial quality, so they have the right kind of shielding and filtering and other features that you need for a deployment. The comparison between the state-of-the-art microgrid controllers as we understand it versus our distributed approach is that we try to implement this in an open source framework. We strive for completely distributed and resilient implementation. So there is no single point of failure in the system, so to speak, and should be easily configurable for different microgrids, including nested microgrids or multiple microgrids that need to be connected together. Because these computing nodes are taking up the responsibility of the interface between the logical network and the physical devices, inverters, and so on. They are easily configurable to interface with legacy systems that use a variety of protocols. And the connection is very close, so there are no problems with long cables or long connections to a central control room. So our work is situated on level 2, so to speak. We assume that we have lower level functions that are implemented by high frequency controllers. So on the lowest layer, we assume a genset controller, we assume a battery energy system that has its own inverter. We assume a photovoltaic system that has, again, its own high frequency local controller. And our system comes on top of this, which implements the level 2 control algorithms. So in microgrid domain, there are typically two categories of control algorithms: the transition functions, when we want to go from grid connected to islanded or vice versa. And of course, the dispatch functions, where we want to stabilize and maintain stability in the microgrid and maybe connected to the main grid or in an islanded mode. So we are in the middle of this picture, so to speak, and focusing on this level 2 algorithms. The physical deployment, what we envision is, once again, these REAPS nodes that run the controller algorithm on top of this distributed operating system, talk to the local devices using industry standard protocols. In our demonstrations, we are using Modbus. We experimented with CAN bus protocols, but there are other opportunities as well, of course. On the other side, they are connecting to a standard industrial internet at TCP/IP network to exchange messages. This distributed operating system, this REAPS layer, has a number of software services. So it's like a miniature cloud computing platform that helps with implementing, deploying, and managing distributed control algorithms. The algorithms are built from reusable components that interact with each other using messages. And these network messages, we support a number of paradigms, publish, subscribe, synchronous and asynchronous remote method invocation, and so on, that are prevalent in distributed applications. But in addition to this, we have a way of configuring these applications from modules. We have fault tolerance capabilities, automatic restart, fault monitoring, resource monitoring, and resource control on the individual components, as well as distributed algorithms that help with time synchronization, coordination across multiple components in the system, for example, fault-tolerant voting algorithms, as well as other things that you need for bookkeeping. So deploying the software, restarting the software, remotely managing the software, and of course, support for security. All the communications are encrypted. We have ways of protecting the network against external attacks and similar malevolent behavior. So how do we test this? In the project, in addition to Vanderbilt, my colleagues at North Carolina State University in the Freedom NSF ERC have a pretty sophisticated power lab where they have power equipment as well as real-time simulators. And in this setup, what we used for the application testing itself, we are using Opal RT with a model of a prototypical microgrid. I will show it in a moment. As well as we built these embedded controllers using off-the-shelf hardware embedded computing devices connected up the two. And we use this configuration for real-time testing of the actual application software. So the simulation is real-time, so it's cycle accurate, and it's showing what power system would do. And we can measure the performance of the controller on their real-time constraints, of course, and how well it works in conjunction with this physical implementation. The testing what we are doing, we do this with the help of the Banshee model. So Banshee came out from MIT Lincoln Lab, and other participants created this microgrid network model, which is shown here. As you can see, there are 3 feeders that basically feed 3 microgrids that could be integrated and could be treated as a single unified microgrid, but also they can be disconnected from each other. And in this case, you have 3 independently operating microgrids. We made some extensions to this. We added a couple of PVs and generators to make it a little bit more realistic. This is the example that we use. Now, the good thing about this is that there are OpenRT models for this, high fidelity models. And they also have the simulated low-level controllers that we interact with using standard Modbus protocols. So if an inverter is available on the model, we can talk to it using our Modbus implementation and directly perform the control actions. During the previous phase of the project, we have developed a number of test cases. And on this chart, I'm showing the one test cases that we have executed, and we performed the testing of these microgrid control algorithms. Once again, some of the control algorithms are related to grid-connected operation. And there are 3 examples here: real and reactive power dispatch at the point of interconnection, grid support. So this is when the microgrid is asked to support the main grid and provide power for it, as well as power factor control at the point of interconnection. So we created, based on these models, the algorithms, and these distributed algorithms, deployed it on the platform and ran them in these tests. The algorithms themselves, what have been implemented with my colleagues at North Carolina State, they are primarily based on a consensus algorithm. The consensus algorithm is actually converging very, very quickly, and we are able to control the microgrid. I will show a couple of results soon. Within the required constraints and parameters. We run at about 120 millisecond cycle time with these second level controllers, and it seemed to be working quite well. So we implemented a number of control modes for planned and unplanned islanding. Again, I will show in a moment. And we also run a couple of tests for islanded operation, where we are connecting adjacent microgrids to each other. So basically what would normally be on separate feeders. So here are some results. This is a power dispatch example at the point of interconnection on feeder 1. And at the POI, we want to control the power to follow some reference. The upper part of the diagram shows the real and reactive power at the POI and how it changes. The next segment shows how the battery systems and the genset 1 that we have in the model is providing power as the required real and reactive power changes over time. Now, here the trick is that the battery and the gensets have some ratings, and the ratings may be different. And what these algorithms can do is that they share the power according to the rating proportionally among the different elements. So in this particular example, the batteries are 1 MVA and the genset is 2 MVA. We also have a PV in the system, and the PV output is rather high, but it's rated at 2 MVA. So this shows that the control algorithms are able to implement this proportional power sharing in this mode of operation. The next example, and in the interest of time, I'm jumping ahead, showing what happens if we have an unplanned islanding on feeder 1. So what happens here is that all of a sudden we got to disconnect from the main grid, and we have to stabilize the microgrid rather quickly. So you see at around 10 seconds starting from the test beginning, we have a unexpected disconnect event, in which case the real reactive power coming from the main grid all of a sudden drops to 0. That's on the second diagram. The battery and the gensets kick in, and after some transients, they stabilize, as it showed, and we are able to remain with the frequency within the required frequency range, as well as with the rating requirements of the individual DERs that we have on the network. So this is an example of what happens if all of a sudden we have to disconnect, and the algorithm kicks in, and once again after some transient, it stabilizes the microgrid itself. So this slide shows another test side by side, better to say two. One of them is a planned islanding. The other one is the unplanned islanding that I showed before in another configuration before. So the planned islanding, of course, means that we have a forewarning where the utility tells us that the microgrid has to go offline or has to be disconnected from the main grid, but we have some time to do that. So in that case, we kick in the controller and gradually regulate down the power at the point of interconnect to 0, so that the disconnection can happen. So the left side shows this transient period, what we have time for, because we have a forewarning for this disconnect. And the algorithm kicks in, regulates it down to 0, and stabilizes the microgrid, and then the disconnection happens. On the right side, this is the abrupt disconnect, and we are able to handle that as well. So the project has still a number of remaining tests that we want to perform. So one of them is what happens if we are in a grid-connected operation and we lose a bus. So in this case, we have to rapidly adjust the distributed controller to pick up the loads. And the other two tests, which we actually have most of the work done for this, are the transition tests. So grid connected to islanded, together with a loss of bus, as well as the islanded to grid connected transition, where we are reconnecting to the main grid. So when we are reconnecting, the algorithms regulate first the voltage, then the frequency, and finally the phase, so that the microgrid starts tracking the main grid. And after these 3 stages, it is able to connect with the relays to the feeders and work together with the main grid. The project also has some tests that we still need to perform for cybersecurity capabilities. So these are the classical confidentiality, integrity, authenticity, and availability tests. As I said, the platform has software support for this, but we need to test this with in the context of the actual power grid application. So what are the benefits for a microgrid operator? In the first example, what I showed is reactive power dispatch. We have precisely controlled power flow between the utility and the microgrid, and we can also support optimal power sharing among the DERs that are in the microgrid itself. So these are following their ratings. In the second test, which I haven't shown the results of, we can support the grid. So the microgrid can supply power to the utility grid if necessary, and we are able to control that. We can also do power factor control, and with the help of the microgrid, we can control obviously the phase angles and so on. Can influence the phase angles, better to say. So the power factors are as necessary. In the planned and unplanned islanding mode, we have support for this control transition if we have the message from the utility. And of course, if it's an abrupt unplanned islanding, we can do a safe transition if it is necessary because of an emergency. And of course, in islanded operations, we can connect and disconnect adjacent feeders and form, from those three microgrids, a single integrated one, or keep them operating separately. So these are just a few advantages. And one important experience that we had with this distributed algorithm was that, okay, what happens if a node drops out? It turns out that the remaining nodes with the distributed algorithm, they are still able to stabilize the microgrid, but probably the quality of control is not going to be as good as with the node participating. Now, of course, if you don't have enough power on the microgrid side and loads are still still connected, sooner or later we have to do load shedding. So we have some algorithms that we plan to evaluate and test, so that on the microgrid side we can also do load shedding automatically based on, let's say, some priority scheme. So in this distributed microgrid control implementation, we enable optimal economic power sharing, seamless and safe transitions between the different operating modes. We can control power factor, and we can do coordinated operation of connected microgrids. We believe that this distributed approach is a new paradigm that can improve operations and reduce costs. It's a completely decentralized control lab. You need a network, a computing network, to connect the nodes, but other than that, the individual devices are rather simple. And this implementation, what we are building, is I would say about 75–80% complete. And we aim to use it as kind of a reference implementation that can be used for constructing specific installations. So what are the benefits to DoD independence? So installations can be supported by their own microgrid. We can provide resilience. In case of the emergency, microgrid can operate autonomously. We have flexibility. The operators can choose to rely on the DERs or the utility grid based on conditions, maybe economics, and optimality, because the DERs, we can optimally utilize them. My team consists of my colleagues here at Vanderbilt. So research scientists, engineers, as well as graduate students. And at North Carolina State University, we have Professor Lukic, who is the co-PI on the project, and faculty and postdocs and graduate students participating. So thank you very much for your attention. And this is my contact information, this is my email and phone number. And feel free to contact me if you are interested in further details about the project. So again, thank you for the attention.
All right, thank you, Gabor. We do have a number of questions that have come in, and if there are any others out there to the audience, you can submit them at this time. First, has this work been tested on real hardware in a military installation context yet?
No, the answer is no. So right now, NCSU has this high fidelity simulator but in the next 6 months, probably we are going to hook it up to a lab microgrid, which is much smaller than, of course, than the Banshee one, but it's a real physical system. But the answer to the question whether we have tested this in a military installation, the answer is no.
Okay. And how portable is the system beyond the Banshee network?
So the system, the software is, I would say, pretty portable, because the software itself has, does not have a built-in model of the microgrid. You can supply a configuration info. You have to supply configuration information for the software, like the names of the relays, or what is the address of the Modbus connected inverter, and things like that. But other than that, the algorithms are pretty, and the software is pretty portable to arbitrary microgrid configurations. Now, one caveat: if the microgrid has DERs which have a special protocol, we probably need to develop an interface component for that, as a piece of code that basically connects that protocol. But the algorithms themselves are generic. So these are mathematical algorithms.
Okay, perfect. Thank you. Do you have a way to protect or sense spoofing of dumb sensors, such as temperature or pressure sensors on devices? For example, those that are on transformers.
So we have not done that. I would say that the software implementation makes this possible, but we don't have, we did not develop algorithms to do this. The way I would do it is to rely on redundancy. So if I have ways to measure, let's say, temperature of the oil in the transformer or something, as well as the power flow through the transformer, then correlating these two measurements, I can use something that's maybe a spoofed sensor. The other thing what is doable in software, I believe, is to use analytical redundancy. So if you compare measurements from adjacent nodes in the network, you can detect if there are some issues with the sensors. So it is possible. We have not done it.
Okay, thank you. And I probably have just one more question for you before we bring Fran back on the line. Gabor, can your system do black start?
Very good question. Yes. We are working on it. So we worked out a scheme for bringing up the microgrid from in a black start manner. We haven't implemented it yet because of the time, but in the next period, we would like to test that out. So we have an algorithm, but it has not been fully implemented and tested yet.
Thank you. And Fran, if you'll come back on the line, we have a couple of higher level questions to wrap up.
I'm here.
Hi. So the first one is for you, Fran. Would you describe the main challenges of implementing model-free reinforcement learning in microgrid control?
I think there are several items I want to mention. First, when we implement this, especially implement this in the real system, we need to make sure it doesn't interfere with the normal power grid operation and security. So many times we you start with a simulation environment because initially it's kind of like a try and error search. Okay, so we start with the simulation for training, and then once we, with a reasonably good system model, then once we reach a good initial value, then we place this in the grid for a real operation. So basically the point is to follow the grid security requirement during the testing and the implementation process. Secondly is the challenge is if we take a non-model based analysis like we did in one of the slides. So then it's more or less like a random search in a huge searching space. That effort, even for the training, will be huge. With model based analysis, it will significantly reduce our training effort. And however, this model-based analysis will be problem specific. For example, if we want to do it for something else, then you need a good domain knowledge for that area. So that's the two items I want to mention.
Okay, great, thank you. And Gabor, would you please, as we wrap up here, describe your plans for technology transition, the steps for the technology to be used at an actual installation?
Yeah, so first of all, we would like to test it on a hardware environment at North Carolina State, and my colleagues working on that, as well as local partners at North Carolina who are building microgrids. We also reached out to colleagues at Fort Campbell, Kentucky, which is very close to Vanderbilt, and we started some discussion with their microgrid folks, who are actually it's a contractor who is building their managing their microgrid. And we also have a startup that hopefully will take up the support work and facilitate the actual transition. So it's a little bit tricky because this is software and algorithms and their implementation. But the plan right now is to team up with a firm that is actually building and deploying microgrids and work with them to transition this technology in field installations.
Great. And Fran, would you please summarize the next steps in your project?
We will continue the hardware in the loop test with RTDS system jointly tested with Missouri University of Science and Technology, and then that's the main next step. Yeah.
All right, at this time, I'd like to thank both of our presenters for today for the presentations as well as answering the questions. Thank you.
Thank you.
Thank you, my pleasure.
And in this series, our next webinar will be on Thursday, August 11th. That one will feature DoD-funded research efforts on characterizing and treating PFAS source zones. Registration is open, so please visit the SERDP and ESTCP webinar webpage to register for this and all the other webinars through February 2023. Before we conclude, I'd like to remind you that both the audio and a copy of the presentation from today will be archived on the webinar webpage in case you want to refer to them in the future. We would appreciate it if you could please take a moment to complete the survey that will pop up on your screen at this time. And this concludes today's webcast. Thank you all.